Alright, now we look into the week 7 matrix algebra for homogeneous linear algebraic equation. So the homogeneous here represent the equation that is equivalent to 0. So that's what we call homogeneous. Just now, the previous video is actually on non-homogeneous, meaning that your linear equation equivalent to a number. So what happens if you have the linear equation that is homogeneous, meaning that it is equivalent to 0, okay? So multi-component system result in n set of mathematical equation that must be solved simultaneously. It can be represented in the matrix format. And if B is equivalent to 0, meaning the answer is equivalent to 0, it is called the homogeneous system of linear equation. Right? So, first of all, when you get the linear equation, you have to check whether they are homogeneous or non-homogeneous. So again, I repeat, the homogeneous meaning that all equation is equivalent to 0. And that's number one. And number two, okay, and then you check whether the determinant is not equivalent to 0. If it's equivalent to 0, you cannot solve using Cramer's rule. So you have to use row equivalent format and Gaussian elimination format to reduce it until you get an answer. Okay, so that's the rule that we already covered in week 6. Okay, so now we look into the same technique to solve the linear equation, but then again, now the situation is a bit different where all the linear equation is equivalent to 0. For example, like this case, for example like this case each equation 1, 2 and 3 are all equivalent to 0, so meaning that this is the homogeneous system. Okay, so depending on the coefficient matrix that represent any physical system or application, if coefficient matrix is this one, coefficient matrix equivalent to 0 and B is equivalent to 0, the solution here is equivalent to 0, then the solution for X due to the initial and boundary condition are non-zero, which is non-trivial. But if C is not equivalent to 0 and B is equivalent to 0, then the solution X due to the initial or boundary condition are 0 or trivial. Okay, so in this study, let's focus on the term what we call the eigenvalue and eigenvector in order for us to find the solution for homogeneous equation. Alright, so in the situation where we have the homogeneous equation like that, so we can solve it by multiplying the eigenvalue and eigenvector to the matrix in order for us to get the result. So I'll look into the eigenvalue and eigenvector problem. So this is one of the example of why it is needed the eigenvalue and eigenvector, where we do have what they call a spring system that equivalent to 0 when we want the system to be stable. We need to put the equation is equivalent to 0 as shown in here, and from that we can solve it by multiplying the matrix with the eigenvalue multiplied with matrix identity in order for us to solve the eigenvector after that. And by comparing the general formulation of the eigenvalue and eigenvector, and that will determine the answer, because your answer won't be an exact value like equivalent to 2, equivalent to 3. It won't be that value. It becomes a vector, eigenvector value, and it is belong to a parameter, another parameter that we can solve it. Alright, let's look at the example so that it makes sense on what exactly that what I explaining just now. So solving the eigenvalue and eigenvector problem, let's look at this example. For example, that we have the situation from previous example, I think, from the previous example at the top. So you have 10 minus w squared as shown in here. So it has the non-trivial solution where the x1 and x2 is not equivalent to 0. So determinant of this must be 0. So in order for this situation to happen, the determinant needs to be 0. And let the eigenvalue become lambda minus omega squared, and you replace the value of omega squared here with lambda. Okay, so from here you find determinant of this equation. So how you find determinant? These two you multiply together, minus 25. So when you expand, you will get lambda squared minus 20 lambda plus 75 equivalent to 0. Okay, so this is what we call the characteristic equation. So from here, you solve the characteristic equation. Okay, when you solve the characteristic equation, you will get, this is the power of 2, so you will get two solutions, lambda 1 and lambda 2. So when you solve it, you will get lambda 1 equivalent to 5 and lambda 2 is equivalent to 15. So this is what we call the eigenvalue of two mass spring. So now, after you get the two eigenvalue, lambda 1 and lambda 2, now lambda is actually omega squared. So lambda 5 omega squared, this one, the first case is square root of 5. So that's why you get it here. So there are two cases of eigenvector. One is lambda 1 square root of 5, another one square root of 15. Alright, okay, so you can solve it. This is lambda 1, this is lambda 2, square root of 15. So you can solve it, the equation, and you will see that your your solution now depend on one value of t actually. So this one is the concept of eigenvalue and eigenvector. Hold on, let me. Alright, now let me move to the second part, which is the second mode where the omega is square root of 15. Sorry, this one is correct actually. This is omega 1. Okay, so that's the answer. So when the eigenvector is equivalent to 15, omega 2 is actually square root of 15. So you can solve it and you will get the answer is equivalent to this. So it depends, your system is depending on the value of roots of the characteristic equation. It depends on the eigenvector value. Eigenvalue for each particular case. So similarly, you can have a look at the example in here. This is for you to read, not to worry on the concept actually. It just almost similar as above, with just the presentation only. Alright, now let's look into 3 times 3 matrix. The 3 times 3 matrix is the one that we are interested on. So assuming that this matrix is the homogeneous form of equation. Okay, so first, we need to find the eigenvalue and eigenvector for this following matrix. What you need to do first, you need to form this matrix first. Lambda I multiply with x equivalent to 0. So this is matrix, this is matrix, this is matrix A, this is matrix identity. Okay, so what you need to do, this is matrix A, this is matrix A, minus lambda, matrix identity is like this, multiply with x1, x2, x3 equivalent to 0, 0, 0, because this is homogeneous. Okay, so here is there's no component in 0, 0, so you remain as it is, but in the diagonal part you will get lambda here. And then after that, you find determinant of this matrix. So you need to find determinant of this matrix. So you do it for this part and so on. So you will get the equation like this, and you solve it, you will get the equation to power of 3. So you can click calculator to find the roots of the equation. Okay, this root of equation is actually the eigenvalue. And you have to remember, when you are factorizing the equation that has power of 2, power of 3, if you have a quadratic equation, so you will have two roots. But if you have cubic equation like this, power of 3, you will have 3 roots. Okay, so if you click calculator, you will get only 2 roots, meaning that one of the roots are repeated roots. Okay, for this case is what they call negative 2 is the repeated eigenvalue case, which is repeated root. Another one is lambda 3. So you solve one by one, the eigenvalue that is case 1 and case 2, which is negative 2. You replace back the value here, the lambda. Now the lambda is negative 2, so you replace it here, replace it here. Okay, you replace it here, and therefore you get this value. Okay, so you can augment it like this, and you solve it using forward elimination, as what we covered during week 6. Okay, so at the end you will get, at the end you will get this kind of equation. Okay, where there's no exact solution. The x1 is depend on the value of x2 and x3. So you can leave it as it is, like this. X1 is x2 minus x3, and x2 and x3. So of course you can replace the value as shown in here, but let's say if the lambda is this case, and you can replace it like that. But if you remain it like this also correct. Okay, so now let's look into the eigenvalue that is equivalent to 4. So you replace the eigenvalue equivalent to 4 to here, to this one. To this one. So you will get this is the matrix, and then you will get this answer, augment it with the 0, 0, 0, and then you do forward elimination. You will get the, based on that eigenvalue, which is lambda equivalent to 4, you will get the eigenvector as shown in here. So actually this is in terms of this, but you can replace the value, let's say as 3 equivalent to t, and then you can replace it as it is like this. But if you leave it like this also correct. Okay, so this is what the final answer. It depends on, meaning that your solution does not depend, it's not unique. You have a situation where you can replace the value based on the parameter that you set in, meaning that let's say this one is your x1 depend on x3 and so on. So you can form the answer like this. This is for this case. Just now you get 110, 110 as the answer, 110, negative 101, and then here is 0.5. So we can combine it together as well, the eigenvector, like this one. You can combine it. It become like this. This is eigenvector, and spectral, this is the eigenvalues. Okay, and you can do the verification. If you multiply with what you call vector diagonal, you will get back the answer. So that the vector diagonal, I go it quite quickly here because it's not that how to say, it's not that critical for your exam, but it's good for you to know, and for you to be able to do the assignment, and as well as what you call tutorial. So diagonalization, meaning that eigenvector are useful to diagonalize the square matrix. So you can use the previous concept of eigenvalue and eigenvector to form a matrix, and from that you can get the diagonalization matrix. Okay, so the formula is like this actually. The matrix multiply with its inverse, you can get back the matrix itself. Okay, so this one you can read it on your own, but that's not really critical per se. And also the same concept can be used if you use Cayley-Hamilton theorem. It says that, okay, Cayley-Hamilton theorem is very useful if you want to solve higher order of metric. So from the characteristic equation that you get based on this formula, you get the characteristic equation, right? So characteristic equation you will get in terms of the lambda. Hold on, okay, and this is the characteristic equation that we get from the eigenvector previously. Characteristic equation that we get. So Kelly Hamilton said we can transform this to become a metric. So how to transform to become metric? This eigenvector here can be transformed into matrix. So the lambda become A, here become A. That if there is no lambda, you have to multiply with matrix in the identity. Because A, okay, this is the formula that Kelly Hamilton said. So from the characteristic equation, you can transform into matrix like this. And then, alright, and then, okay, let me rewrite here. Lambda power of 3 minus 12 lambda minus 16 I equivalent to 0. So the, it's just 16. So the Kelly Hamilton said that you can transform it to become matrix. So it become A power of 3 minus 12A minus 16. There's no lambda here, right? So this is equivalent to I. So now after you get this, you can divide this or multiply with 1 over A. So A3 divided by A, you get A power of 2. This one you get A. And A multiply with A inverse, you get I. Okay. So I divide by A from here, A inverse. I divide by A, you get A inverse. So 16 A inverse equivalent to 0. So the A inverse is equivalent to 1 over 16 A squared minus 12I. Okay. Okay. Right. So from here, A inverse is 1 over 16 multiply with the matrix A 2 times of matrix A. This one. 1, negative 3, 3, 3, negative 5, 3, 6, negative 6, 4, power of 2, minus 12 multiply with 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so you will get the answer is 1 over 16, negative 11, 3, 6, negative 3, 17, negative 17, negative 6, negative 3, 3, negative 8. So this is another way of you finding the inverse matrix using Kelly Hamilton theorem. Okay. So again, I repeat, using this concept, you will get the characteristic equation. From the characteristic equation, you transform it into this format, and after that, you multiply with 1 over A, and you solve it by replacing the value of the matrix. Okay, sorry. Okay. So the same concept can be used to do the verification of eigenvalue and eigenvector as shown in here. You can read it through here, but it's not that important. Not to say that it's not important, but then again, it's for you to know rather than to memorize or focus on this, because the matrix topic is only covered for the assignment. And assignment is already uploaded on Spectrum. You can have a look at it. Okay. All right.